Hello, my name is Murad El-Arbi. In this tutorial, we'll see how to make a polynomial curve fitting program. The tutorial layout is a polynomial equation. We'll see the linear system of coefficients. We'll have an example to solve by the program, which will be as a script, and then we'll transform it into a function. Finally, we'll plot the data pairs of the example versus the polynomial curve obtained by the program. First, let's see the polynomial idea. Here we have a polynomial that will be used in fitting data pairs given to us in a problem or obtained from lab data or so on. So when we have m points or m xy data values, so they would be fitted by the polynomial curve of degree n, and n is selected according to the trend of the curve. That means we need the best fitting curve, so we may try some 2 or 3 choices of the polynomial until we get the best fit. A system of linear equation is formulated to compute the values of coefficients. So actually the main target of this work is to compute the values of a1, a0, a1, a2, and up to an. And for that reason, we will create a system of linear equations like this system, where we have coefficients matrix and unknowns vector. So this vector actually is the values of a0, a1, and up to an as the coefficients of the polynomial. And finally, we have here a vector of constant terms. So here we see the matrix, the coefficients matrix of the system, of the linear system. The first element, a11, a capital 1, is m, is the number of the data pairs, while the other elements are the sums of x to different powers. So x to the power 1, x to the power 2, and here we notice that this is the sum of all values of x raised to power 1, for example. Here, for example, every individual element should be raised to power 2, and then the sum takes place, and so on. So actually we are summing the values of x raised to power of the location. As we see, there's some location, will a relationship between the power and the location in the matrix. Also here we see the terms of y appear here in the constant terms vector b. So we will find a relationship that enables us to program the formation of this system. Here also we should notice that the summation signs or means that we are summing the values from I1 to m. That means we are taking the sums of all given x data. Also here we should use the values of all y data. So all the values given in the table or obtained in the lab should be involved in the computation of the coefficients and values in this system. Now, if we concentrate at each element here, we shall notice simply that there are relations between the power of each x term in the matrix A and matrix B and its location or their location. For example, in the matrix A, the power can be represented by the row number plus column number minus 2. For example, let's examine it here. Here we have the first row, second column, and the power 1. So 1 plus 2 is 3, minus 2 is 1. So here we have x to the power 1. Let's take this element, for example. Here, the second row number is 2, column number is 3, so 2 plus 3 equals to 5. 5 minus 2 is 3. Here, for example, this is the row n plus 1, because here, if we start here from x to the power 1, so up to the last one here is n, that means the number of rows is n plus 1. So here, for this element, the row number is n plus 1. The column number is 3. So n plus 1 plus 3 will be n plus 4. n plus 4 minus 2 will be n plus 2. Finally, let's see the last element here. So we have the row number n plus 1, the column n plus 1. So n plus 1 plus n plus 1 will be 2n plus 2. 2n plus 2 minus 2, 2n will be equal to 2n. So this way, all elements except the first one, except a11, all elements follow the rule of row number plus column number minus 2 for the value of the power of each x in the matrix. For the constants vector, the rule is row number minus 1 for x's. So we see here, for example, here we don't have x. Actually, here we have x to the power 0, because the row number is 1. 1 minus 1 is 0. So x to the power 0 is 1. So always we assume that yi here is multiplied by 1. Here we have the second, we are in the second row. So row number is 2. 2 minus 1 is 1. So here x to the power 1, and so on. Here, for example, n, we have the row n plus 1. So x to the power, so n plus 1 minus 1 is n. So this is generally the rule of, or to determine the powers in terms of the rows and column number. Here we have an example. If we have a polynomial of third degree, or if we want to make a polynomial of third degree, so this will be simply the configuration. We'll have 4 rows and columns, so the system size will be n plus 1, and then the powers will be 1, 2, up to n, which is 3, or here, for example, 1, 2, 3, and 2n will be 6 here, and so on. So actually, it's simply we can figure out the, or get the values of the powers of each element by using simple mathematical relation. Once all coefficients of the matrix and the vector of constant terms are calculated, the system can be solved by using linear system solving technique. In MATLAB and Octave, the backslash operator is used to solve the linear system. Here we have this example. So now we'll start coding the method in order to solve, or in order to get a polynomial which fits this data set of xy values. Now let's go to the our editor and see how to code this system. So first, we should define the values in our script. We'll say x. So we see here that x values start from 0 to 5 with step 1. So simply can say from 0 to 5. So this is the values. This is the array of x. Let's define the array of y. Start 2, 8, 14, 28, 39, and 62. Now we can define the value of m, or get the value of m simply, the number of the points, by the function of MATLAB Octave called length. So we can say here m equals to length x. So also you can say length y, because we know there are data pairs, so actually the number of elements in x must be equal to the number of elements in y. Now let's define what n, the number or degree, sorry, the degree of the polynomial. So at the beginning we'll take the square, or let's say quadratic equation, or polynomial of degree 2, and after that let's define the matrices and vectors required for solution. So A will be zeros. This is in order to open or to create here n plus 1. So this is n plus 1 by n plus 1 matrix. B is a vector, so it's zeros. Number of rows is n plus 1, and number of columns is 1. A small also is a vector, so n plus 1, and number of columns is 1. So we defined the number of, or let's say we defined the components of the mathematical solution or numerical solution for this problem. Now let's start the loops. So since we have matrix, so the matrix needs 2 loops, loop of rows and loop of columns. So let's say here for row equals to 1 to n plus 1, because we have n plus 1 rows, and for column equals 1 to n plus 1 column. Now we will start filling the matrix A and the vector B with elements, and then we'll solve the system. So first of all, the first element, let's go back to show you the okay, so you see here in the upper right corner the system. So the first element is m. So at the first step, at the first, let's say, loop, we will assign the value of m to the element a11. So here we should make a condition, because it will happen only once. So we say if row equals to 1 and column equals to 1, then A row column, this element, you can write A11 also, no problem, equal to M. Now, we should write here continue. Why? Because after this condition, we will compute the values of A row column of the whole system. But if we don't skip this line, this definition for the first time, so if we don't make continue here, this will be computed, and then the value assigned because of this condition will be lost. So we make a continue here. It will be made once, only once, when row equals to 1 and column equals to 1. So for this reason, we should compute A11 only once. If we don't make skip or continue statement here to skip this step, the value what would be assigned to A column 1 1 again will overwrite the value assigned by this condition. So we should be aware about this point. Now sum, because we have summation, so use function MATLAB Octave function sum. So we say sum x to the power. Notice here I used dot 1. Let me enlarge in order to have better view for so here I use dot power instead of power. Why? Because I want to raise every element of x individually to the power computed by the rule here, row number plus column number minus 2. So here I should write row plus column minus 2. So this is simply the definition, or let's say the computation of element A. Now A is a matrix, so it has rows and columns. So we can end here the loop of columns because we computed the values of A, and start computing values of B, which has rows only. So here B row will be equal to sum again, because we have some signs here also, we have sum of x to the power, according to the rule here, row number minus 1. So we say row minus 1 multiplied by y, individually by y. So this is the calculations of values of B. Finally, we end the loop of the rows, and we say that A small goes to A capital backslash B capital will yield the solution. Now this is the code. Let's save this file and try to run the code in the command window and see the results. So we have those results obtained, but I think there's something wrong here because doubtful about these values. Oh, here's a mistake. Yeah, okay, only one again. Okay. Actually, this is very critical because this type of errors cannot be caught by the interpreter. So you have to be aware about the values. Since I previously solved this equation or this example, so I expected the values. So the minus sign here, those values are not the correct. So let's see. Again, CLC and run the code in order to see a right value. Okay, now we have those values. These values are the coefficients of the polynomial. But this shape of output is not so explanatory. It does not explain exactly what is the coefficient of which term of x in the polynomial. So let's make some small addition of fprintf function here and make some small addition of f of x equals to, let's say here, f. Here, let's first step, let's print the constant term, a1. Then let's make a loop for, let's say, I equals to 2, because this is a1. We have 1 here, so we start 2 to n plus 1, and f print f, then we'll say plus f multiplied by x to the power d. We'll see the result. So the coefficient a I, and here I minus 1. And let's say end. Now let's run the code and see the result. Okay, now as you notice here, the f of x, let's close this. Now this is the result as you see in the command window. F of x, this is just print. This is just a print out method. It's not exactly related to the values of the solution because we already obtained the coefficients, but just in order to make the result more mathematically readable, we can make it like this. So here every coefficient is multiplied by its x to the power or 1 or 2 and so on. So let me modify because we don't need the, sorry, here. I think I'd better to, okay, let's try this. Okay, also in order to make the prompt, because here's a mistake, because the prompt should be at the beginning of the line. So let's do here f print f and use the escape character of a new line. This is the escape character of the new line. That means print or make a new line. As you see here, the prompt of the command window became or appeared in a new line. Now, we have ended the mission of making the script. Now, let's plot the result. So we have A here. Sorry. We have X, we have Y, and we have A. But there's something important. Let's begin before that. Let's plot the points X and Y, and I will plot them as red circles. Label X label, X, Y label, Y. So let me enlarge the window here in order to make it more obvious, and put it here. So actually, as you see here, we obtained a graph. This is a plot of the points. We still didn't plot the curve, but these are the points of the given data. So these are the points of the given data, as you see. Now, let's plot the curve. First of all, let's create an array of X, and we know the data from 0 to 5, but in order to create a smooth curve, let's take a step size of each point in this curve as 0.1. So it will give us a smooth curve instead of a line of 5 points. It could be straight lines. So generally, we should increase the number of points for this curve. Now, then we want to compute YP, where YP are the points generated of the curve by the obtained polynomial, the polynomial which has these values. So here we can say that YP will be equal polyval, where polyval is a function. So we can say for here YP equals polyval, and we will use A. But there's a problem. In MATLAB, we have a library of polynomials, but the sequence of the polynomials in MATLAB, or the system of polynomials of MATLAB on Octave, is different than this one which defined in this tutorial, or by the curve fitting method we used here. Let me go back to the slide, the first slide here. The order here starts with the constant term, and then term x to the power 1, x to the power 2, up to x to the power n. While in Octave, and MATLAB, the sequence, the largest power is the very beginning, at the very beginning. Then it will be x to the power n minus 1, x to the n minus 2, up to a to the power, or x to the power 1, and then the constant term. So in other words, we should reverse the order of the power terms of the polynomial we obtained in order to be able to use the function polyval. So simply, it's a very simple solution. We can say here a and minus 1 to 1. That means start a, the coefficients of a, but instead of taking them normally as they are, no, take them reversed, or make it the sequence start from back to front, start from the end to the first element. And then here, let's enter the values of xp, because we want to compute yp corresponding to every value of xp. So we should enter the array xp here. Okay, forward. I forgot to put the semicolon. Now we computed all values of yp corresponding to the xp for the curve. Now let's plot xp yp. Okay, as you see, we obtained this curve. Actually, here's I forgot to enter hold on. So again, let me do something. Hold on, and let me plot. Okay. Okay. Now, maybe it's obvious that we plotted the curve. This is the blue curve, is the polynomial curve, and these red circles are the given data. So you can see here that the square, or let's say quadratic equation, the quadratic equations, because our equation is a second order or second degree polynomial, so it's a quadratic equation, gave us a good fit for the given data. Now let's try to solve the problem by using the third degree polynomial. So we go to the editor. Let me here make the window smaller in order to make it much, and change here the value. You see, we'll change the value to 3, and then run the code. So here we obtained, as you see, a third degree polynomial. So we have the values of f of x, or let's see, the f of x, we have the constant term, and we have zero term here. So actually the zero term means that we don't have x square term, so it will be directly 1.92 plus 5.6x plus 0.25 x cube. So this is the solution. Now let's repeat the same procedure. So we say yp but this time we will take polyval A. Again, we reverse the values, so end -1 to 1 for all values of xp. Compute by using this polynomial, compute the values, corresponding values of yp to xp. And then we'll say plot. Actually, we have hold on before, so this plot will be shown over. And let's change the color. So let's say the color black. Dashes in order to now let's enlarge the window for you, and you see here that we obtained another curve of dashed lines, which is the cubic polynomial, or the third degree polynomial curve. So in this way we obtained the result and plotted the resulting solution. Finally, let's use the function, or let's transfer this script to a function, because functions are more flexible in use and application in different scripts and other functions if you want to make a big project to solve or something like that. So let us transform this script to a function. So here I will take out the values of x and y, because they should be passed as arguments to the function. Also, we will take off the value of n, because also it should be passed as an argument. We'll say function a, the value which is a is going to be returned to the user. So a, and let's call the function poly curve fit, because there's a function, there's a library function of MATLAB called polyfit. So in order to avoid making any conflict between our code and MATLAB and Octave functions, let's use a different name. So poly curve fit, and x would be given as a parameter, y and n. Also, functions should not print, because we want values to be returned, not print out. So we should cancel the printing, and we should save as the code with another name, and the other name should be equal, or should be similar to the name of the function. So maybe the save as window is not shown for you now, but I'm going to save as. You will notice it at the tab that the name of the file will be changed. So I call it poly curve fit. So it should be exactly the same name of the function. So as you see here, the name and the tab, poly curve fit, the same name of the function, poly curve fit. Now, how can we use this function? Simply, let's go to the command window, and let's say let's first examine, okay, x, we have values of x, we have the values of y. Now let's say poly curve fit the value of x, the values of y, and let's the degree of polynomial 3. As you see here, the same values which were obtained above are given here. We should notice, of course, this value is a bit different because to the power minus 14 means it's 0. So that means it's 0. We say 1.92, it's the same value here. 5, 6, the same value. And quarter, 0.25. Here also we have 0.25. So actually we obtained the same solution. So it was very easy procedure. And if you have any project or another work needs curve fitting, so you can call the function, this function, polycurve fit, or any function maybe you can name it with another different signature or different name. So it's very, very flexible and very useful. So in here we conclude our tutorial, and I wish you find it useful for your work. Thank you very much for listening. If you liked this tutorial, please give me a like. I'll be happy if you subscribe and share this video with your friends. Thank you again, and goodbye.